Ladies and gentlemen, today we're going to be broaching a key topic, one that's going to occupy us for much of the next week, but importantly, it's going to be a valuable sort of capstone for elements of the course. So this topic concerns conducting machine learning using Spark. And specifically using the Spark ML and the older MLlib libraries. You'll recall that in terms of Spark motivation for Spark, Spark sought as a platform to provide a support for data science as a broad endeavor. And that includes exploratory work, it includes data wrangling and working with data, and it includes, importantly, conduct of machine learning as a key component of data science. Many of Spark's constructs and design were specifically designed to support large-scale machine learning on very large-scale data sets that might have hundreds of millions or billions of rows. And this is not an easy thing. It requires care for putting in place scalable mechanisms in the distributed computing area in terms of keeping memory demands low, in terms of being able to discard computations that are no longer current or needed, and that could be discarded and regenerated easily. It includes the use of laziness in order to process things in a way that doesn't involve arrayifying, sort of bringing big data sets into memory, et cetera. But thus far in the class, we haven't really looked at all at the Spark machine learning interface, which is a key component of delivering value with Spark. And today we're going to be doing that, and that is going to continue through future lectures here. The good news is what we have done already, whether it's dealing with Cassandra or dealing with Twitter, et cetera, are things that lay the groundwork for this. We're going to be in familiar territory with a lot of the constructs, with data frames, data sets, resilient distributed data sets, and with the basic mechanisms for accessing and munging data within Spark. However, there's a set of new concepts that are going to come in, which are reified by the Spark platform and which are very powerful. These constructs, like much of Spark, are conducted in a fashion which is, number one, thoughtful, number two, scalable, and number three, functional. And they make use of principles of functional programming to create a very powerful framework for data science that is recommended both by simplicity and by its power and scalability. So we're going to be talking today about Spark ML and introducing for this second generation machine learning platform in Spark several elements that are in the form of pipelines. So Spark ML is a higher level and more evolved pipeline than is the first generation library MLlib. MLlib is very powerful in itself. It will support older operations. As I recall, it's predominantly on RDDs. We'll be seeing it later. But Spark ML is the second generation framework that supports higher level constructs, the most notable of which is pipelines. And pipelines really simplify your life in composing together the sorts of operations, the multiple stages of operations that often go into realistic data science. So this includes aspects of data wrangling and conditioning, transformation needed to then conduct the machine learning itself. So within Spark ML, we have a number of constructs, a number of concepts that are introduced that I want to walk you through that go beyond things we've already talked about. We've already talked about a lot of relevant things: data frames, data sets. In both cases, these constructs that package things up in a way that's amenable to decomposition across large number of machines, like a resilient distributed data set. But they explicitly consider tabular data that's arranged in columns and rows, and that is in some sense self-documenting. Data frames are untyped, or shall we say dynamically typed. When we use them, we will mention columns by name with strings, and will operate on the contents of that column having specified it by string. We've seen this in previous lectures, $, some string to refer to a specific column in a data frame. And that's all fine and good, but they are weakly typed. And what that means is our type errors are not discovered till runtime. And there's a fair bit of interpretation that goes on that has some performance loss as well. Data sets provide this type-safe way of doing the computation. So we'll be working with both of those types today and seeing how to convert from data frames into data sets. But beyond that, beyond those basics that have followed us throughout our other discussions, Spark, obtaining data and manipulating it in some basic ways, we have a set of elements that are introduced by Spark ML. And the two most central, most important, and most sort of pervasive in their ramifications are this notion of a transformer and an estimator. Okay, and these constructs are combined together in higher level constructs yet, such as pipelines and pipeline models, to good effect. So let's just talk about what each of them is. So a transformer is an object whose job in life is to take in data in the form of a data set or data frame and to produce data as a result. Okay, so it takes in data, it's a data set, a data frame, and you call transform on that data, and it produces data as well. So this might be a construct, for example, that strips out common words from text. So you get to the sort of the unique words of it. You get rid of the articles and stuff, the of and the and a and all those sort of words that probably you find very painful in English. It gets rid of these common articles, common words, and it boils it down to the most salient words. Or another transformer might do something like take in words and capitalize them all. So we canonicalize case, right? That'll be another transformer. The key distinguishing feature is that it takes in data and it produces data. So it takes in a data frame and it produces a data frame, right? Okay. And we all know from past discussions, it's really producing a promise for a data frame, and it can be incrementally performed, et cetera. But conceptually, it takes in data, produces data, okay? By contrast, an estimator, the other sort of key concept, is going to take in data, and it produces a model, typically, but really produces a transformer, of which a model is an example, it produces it through calling the fit method. And the idea here is that this is a potential model, but it needs some data to fit it. So maybe it's a logistic regression that we want to produce, a logistic regression model. But in order to produce the logistic regression model to predict, is this case an instance of a flu-related tweet? In order to produce that model that will classify that, we need to estimate that model. We need to create a fit model. We need to do something to say, I want a logistic regression. We need to take some data in order to create a logistic regression that's fully estimated. And then having that model in hand, we can use it as a transformer. So really here, this is producing, yes, a model, that is true, but it's really as a transformer. Okay, so via fit. Okay, and by so doing, we will then have a transformer that we can apply to data. So the logistic regression model that results from fitting a logistic regression construct will then be able to take in data and put out data. Okay, so that's the basic notion of an estimator. Now, beyond this, we have some ancillary concepts or some supporting concepts. Most importantly for our discussion here, and from a software engineering perspective, we have what are called pipelines here, okay? And a pipeline's job in life is to allow us to it serves as a higher level abstraction to take in like an estimator takes in data and it will produce a model, okay? So a pipeline is an estimator. It's a type of estimator, but it's a higher level estimator in the sense that it will have typically many stages. And some of those stages will be transformers and some will be estimators. So in this pipeline, you might, for example, have something which strips out extra words, which canonicalizes, that is capital letters, it strips out extra words. It then has an estimator which will tokenize the words in a vector form. So we'll ask, is a given word present or not in this text? And that will be an estimator which will be able to apply to data through the pipeline. So pipeline is an estimator. Okay, so this is a subtype of estimator. An estimator composed of transformers and estimators of one or more transformers followed transformers and estimators. Okay, it is an estimator, and a pipeline model is a transformer produced via a pipeline's fit method. Okay, and there should be at least one estimator. Okay, so these are the constructs we're dealing with in Spark as key components. And this will be very powerful when we start using them. It'll spare us a great deal of work. Amongst other things, a pipeline, it turns out, will be used both for the data used to fit a model and data used to verify or evaluate a model. So some of you in the class will be familiar with the notion of cross-validation. And cross-validation involves evaluating a model in a way that's scientifically robust by building it with respect to different subsets of data and testing it with respect to other data not used to build it up, right? And we talk often in machine learning about different folds of cross-validation, 10-fold cross-validation or 2-fold cross-validation or what have you. But in all those, they share the feature that we're taking subsets of the data to estimate the model, to sort of build up a model, and then we're evaluating the model that is built up using other data. And with 10-fold cross-validation, we'll be doing this successively with different subsets of the data being used to estimate it and to evaluate it, right? So it turns out pipelines, by reifying a pipeline, by defining it as a construct, we're going to be able to reuse it again and again for each of those phases, the different folds of the cross-validation. We'll use it, the pipeline stages, to transform the data needed to estimate the model, and we'll use those pipeline stages to arrive at the data used to evaluate the model, okay? And instead of having to tediously re-specify that for the different folds of cross-validation, that will come for free in terms of pipelines, okay? By representing what stages of data conditioning, data processing, data transformation are needed on our data before we can get it into the final state to be used for evaluation or fitting, we can then reuse those at many different places, okay? So we can use them for both the fitting and for the estimation. Okay. And a pipeline model will reside from a pipeline when we fit it to some data, and it will be a transformer. So we'll be able to use it as a model. So it's a model, it's a transformer, it's a higher level model that contains all these stages before it. So all you're gonna have to do is put in the raw data and out will come data. It takes care of all the processing steps along the way, be they, of length 1 or length 20, okay? So these are some of the higher level concepts here. Now my machine today is working extra hard because I'm recording this in 2 different mechanisms, this video. So apologies for the delays here. Pipelines encapsulate a set of these operators, these operations, and it makes sure that training and testing operations occur in identical steps. So these are examples of some of the many elements that Spark provides for data wrangling, data transformation, data conditioning. Okay. Some of them may be familiar to you from machine learning classes or statistics classes. For example, things that normalize data. You take in data, a data frame, and you get out a normalized version of that data frame. Okay. Normalized in the sense that everything is scaled to go from 0 to 1. Instead of from the min, some arbitrary min to some arbitrary max value. There's a standard scaler, which I believe may further scale things so that everything is of a standard deviation of 1. Okay, so, and it has a mean of 0. Okay, I'd have to double check the definition, which is the normalizer, which is the standard scaler. I think that may be right. A bucketizer, I think, puts things into bins. A principal components analysis, as its name suggests, performs PCA. Principal components analysis provides linear transformation of the data so that we end up with data that is described in a most parsimonious fashion in terms of what's possible with linear transformations. So it kind of describes the data in a natural basis for how things covary in the data. There's a set of these specifically for the process of text processing, which is a big element of machine learning with Spark. These include some we're going to be using today. Tokenizers, things that will take text, like a big line of text, and turn it into tokens, specific words that are discrete in there. Things that will count the number of times a given word occurs, a number of times certain sequences, like pairs of words or triples of words. That's the n-gram. Stop word remover, these things for these words that are not terribly significant or unique to this text. Having a vector summary of words. And this is a term frequency that can be used together with inverse document frequency to sort of judge what words are overrepresented in this text compared to text we use to train it. Like if we look at this tweet, what is it that really stands out in this tweet compared to the frequency we look in other words? We see in other bodies of text. Like if we look at tweets as a whole, what is it that's the themes of this tweet that are sort of most distinctive? Okay, so these are some things for transformation and data conditioning, etc. These fit into this framework here. For the most part, these things here are Most of them are transformers. We put in a data frame to a tokenizer that consists of a set of strings, and it will put out a set of strings, each of which is a certain word. Put in a data frame to a count vectorizer, will count the number of times certain words occur, etc. Similarly with these scalars. Okay, so we'll use these in our pipelines. We'll use them to build up data. But before doing this, we will be doing things more by hand in order to see the components that go into a pipeline and to appreciate basically how it works. Okay, so what I'm going to do is call up Zeppelin, and late last night. Actually, no, it was during the day yesterday. So it was in an airport in Toronto. I was doing work on this, and so I have everything fired up here. I'm going to restart Zeppelin, and I'd like to suggest that you folks restart Zeppelin. I want multiple instances of Spark running here. Here we go. Okay. There we go. Okay. And I'd like to invite people to come up to the Spark interface, and we'll get started here. Come on. Okay. Yeah, it was a busy camper yesterday. Okay, here we go. Let's get rid of that for good measure, and I'll restart this here. Okay, and we don't need this stuff up. Okay. Okay, so ladies and gentlemen, I'm going to start a new notebook here. Again, you're welcome to get the one off of the website, the Moodle website. You can download it if you'd like. So it is called, give me a second, I will tell you. It's called something to the effect of tweet classification in Spark 2 _ 1. It should be the last one at the bottom. Oh, I didn't make it by default downloadable. Sorry. Is it text?
The Scala.
Oh, that's interesting. Okay. Well, that's not unpleasant, but I'll go update it with the. Thank you for pointing that out. Those who would like to wrangle it as text may do so, but otherwise I will go upload something to it. Okay, why is my Thunar has died here? Sorry. This is a bash kill Thunar. Even of automated killing of programs here. Okay. Linux is great. You can automate the way of dealing with its flakiness. Okay, so I will go now, put it into, boom. Okay, here we go. And here we go. There we go. It's, if you go and look at that, I will make it only downloaded. Here we are, forced download. And there you go. So it should be the last one, March 27th, 2018, first look at Spark machine learning. Okay. Okay, so I'm going to do March 27th in class session, and we should make this based on Spark. We won't need anything particularly key here. Okay, there's nothing we that we have additionally problematic with terms of munging tweets. So we'll just do without that. Okay. The next thing I'd like to do is we're going to import a lot of different different libraries here. Okay, and these libraries are predominantly focused around Spark, and some of them quite specific to Spark ML. Okay, now I've imported them in a somewhat awkward way in the code there, but basically we're going to import org.apache.spark.ml, and I think I'm just going to import everything from that library. Previously, I'd sort of enumerated them all, but we'll just import like that. Okay. And beyond those, I think what I'm going to do is to import Scala, Scala.io. Okay. We're going to potentially use Scala.io for a few components. Now, the next thing we're going to do is to get some data downloaded on your machines, okay, which we're going to be manipulating as example data from tweets. This is data that I classified for this class a year ago. We could probably update it with new tweets. The character of the tweets is indicative of that era in Twitter discourse, as we'll see. So what we're going to download it from is https www.cs.uss.ca/faculty/osgood/classes with a capital C /CMPT 898 winter 2018 / and again, this might be something you want to copy from the example, health-related tweet text underbar 12/18/2016.txt. Okay, I will move it down so you can see it. There we go. Add file. That should be add file, not add. Okay, and similarly, there'll be just another one of these. Oh my gosh. Oh gosh. Okay, now I'm in real trouble. 2018 health related tweet text to 12/8/2016.txt. There we are. Okay. This is just wrapping for sort of aesthetic reasons. There's no significance to it. So let's add file. Add file, and you want to have another add file that's corresponding text, except it's non-health related tweet. And that should not be tests, it's texts. Texts, not tests. Okay. Okay. So HTTPS, make sure it's in HTTPS ://www.cs.uss.ca/faculty/osgood, all that being lowercase, /classes with the first C in uppercase, /CMPT 898 winter 2018 with the CMPT and the W being a capitalized, and then / health-related tweet text underbar 12/8/2016.txt or non-health related tweets. Okay, this is going to bring down those files onto your machines, okay? And it's going to bring them down so then we can access them with some convenient mechanisms to load in CSV files, amongst other things. I'm showing this so we can deal with arbitrary CSV files. It's a little bit overkill here. It turns out that Spark 2.3, we can, maybe 2.2, but I think it's 2.3, you can open CSV files from an arbitrary URL. But because that's not yet supported in 2.1, which we're using here, we have got to get the file on each machine. If this were being executed in a large farm of machines, each machine would download these files onto it, which would then allow us to undertake the next task. Okay. We're going to read in a CSV file. So spark.read.format, CSV. We're going to say it is no header. Okay. There's no header here. And the option infer schema is going to be, I said false, but and I'll stick by that. It might have been useful to have that to be true for other cases. And then we're going to do .load. And finally, inside of load, you have org.apache.spark.sparkfiles.get, and that whole name of the file. Just get it from up here. The name of the file itself. Okay. This like health-related tweets. That. Okay. There we go. Text. Okay. And similarly, those would be for the health-related, and then there's going to be non-health related tweet text, and it's going to be the same thing except this guy is non-health related. Okay, so having done this, it should read in these and create data frames. I would note that this infer schema, it's a very important thing. If you would change that to true, it'll actually, in general, do a better job figuring out what the contents of the files here. I didn't leave it as true this time, but in general, if you're working with CSV files, you want to use infer schema being true as an option, because we'll do a much better job figuring out the types associated with things. Okay. Next, we're going to take a look at what the types of these things are. Okay, we're going to do print schema, and we'll find that the text within that file is particularly simple. All it is a string. Okay. I've done this in a general way, which will support much more extensive multi-columns, for example, who the user would be, what the date would be, what the tweet ID would be, whether it's a retweet, all those sort of things. We could layer in on this later, but for now, it's just strings. Okay, and we could see it. These are data frames. You'll notice they're data frames. Okay, they don't contain type information. It knows the schema. The data frame knows the schema, but it only checks it dynamically. Okay. Okay. Next, we're going to do a very important thing here. This next component is going to be a key one conceptually. It'll be important in terms of its practical implications for the next few minutes, or the next 10 or 15 minutes here. So one thing is we're going to take these tweets, which are unlabeled. We basically have two sets of tweets, one that are health related and one non-health related. And we're going to label them according to their nature. And then we're going to put them into one data set that will contain examples of both. Okay. So what we're going to do, and I'd encourage you to copy it, it's going to be data frame labeled health related tweets, BF data frame labeled health related tweets. Labeled meaning they're ground truth labeled. Okay. And this is going to be the corresponding unlabeled ones. In this case, it's DF health related tweets. And then we're going to do two things. We'll say dot with column label, and the value will be a literal 1.0. So let me show you what that looks like. Okay, so that's going to add a new column. which is going to label this with as being 1.0 in terms of its whether or not it's health related. More than that, there's one other thing I want to do just for good measure. I'll say with column renamed, it just named this because there's no header in the file. It had no header. It didn't know what the column name was. So I'm going to say the column renamed, whatever that was, underbar C0. There we are, underbar C0. The new name for it is going to be text. Okay. Text of the tweet. There we go. Text. Okay. And we're going to do the same thing for the non-labeled, but you're going to tell me what I should put instead. It's going to be mutatis mutandis. It's basically going to be the same deal, but what is going to be the difference? It's going to be what here? 0. Yeah. So we're gonna label both of them. And the label for the non-tweets is going to be a label of 0. These ones are label 1. Okay. Let's take a look at what they look like. All right. Here we go. Just go take a look. Okay. Here are the labeled health-related tweets. We'll do show. And they'll say, I hate being sick. Eat the best of, I think that's a food. Searches medicine. I have been ill for new vaccine again. Okay, so these are some health-related tweets. The non-health related tweets are a broader group yet. Okay. Things are cooking. Okay. Next, what I'd like to do is to, and I think we'll do this a little bit more efficiently than I did it on my own. We are going to take these two sets of tweets and we're going to combine them into a single data frame. Now that they're labeled, we won't be just mixing and matching them arbitrarily. We're going to combine them into a single data frame. So this is what we're going to do. We're going to say val df, that's a data frame, all tweet x equals, and we'll take those two names, the labeled ones for with health, and we're going to take a union of them with the ones that are, guess what? Are non-health related. Yeah, there we go. Okay, great. So when we take that union, we will see some that are and some that aren't labeled, right? We'll have some that came from the ones that were not health related and some that were, but they're labeled so we know what they were. Okay. And this has a string and a label from both. Okay. Next. Now we're going to do something that I anticipated in final closing remarks of a previous lecture, but never really covered in a real way. We're going to take, ladies and gentlemen, we're going to take this data frame, which is merely dynamically typed. It's a data set of row. It's a generic data set. It doesn't really know what types of data are in there statically. It doesn't know statically, oh yeah, the text is a string and the label is a double. And as a result, it won't allow us to do very natural things like mapping it based on a function that maps, you know, doubles to doubles and stuff like that. It's going to force us to do it through UDFs and et cetera, and it won't be as natural. Nothing wrong with UDFs, but it's nice to have things statically typed so we can discover errors amongst other things. Okay. And it might be able to undertake some optimizations based on it. So this is how we're going to do it. This is how we're going to convert a data frame to a data set, to a typed data set, or in short, an untyped data set to a typed data set. Here we go. Okay, so we're going to define, anyone remember? What do we need to define? Case class labeled tweet. Very simple. Labeled tweet. And guess what's going to be in it? It's going to contain what? Good. Yeah, it's going to have one field for each of the columns, okay? One read-only field for each of the columns. It's going to be text, which is a string, and it's going to be label, which is a double. And I think you have to use the same sort of capitalization, all that sort of stuff. Okay, there we go. So that's our case class, okay? And now what we can do is we can say val ds tweets equals if all tweet text dot as, and guess what goes here? We're going to render this as an example of what? Labeled tweets. Yeah. There we go. Okay. Okay. So now we get out a data set of labeled tweets. Before, we just had a data set of rows, which are of limited descriptiveness. Now we have a data set of labeled tweets, right? Which is a happy thing. And so now we could do things such as map it in ways that, you know, take the square root of the label or what have you, without problems. That puts it into to better stead. So before, if we had tried to do, you know, df all tweet text, and we had tried to do, for example, filter by, you know, label, you know, this dot label greater than 0, or something like that. Say label double equals 0 here. It would say not. Right. So I'm just showing it's going to fail if we did it with data. That's what, if we did it before. Now the world is a happier place, right? By the way, in general, you should be cautious about doing exact comparisons with double values, because sometimes they can be slightly off what you can expect. In this case, for several reasons, it's actually safe. Okay, so now we can do it just fine. We can it knows the underlying type, and then we can do a map or whatever, right? It's all strongly typed now. Okay, so that was converting a data frame to a data set, and thereby bringing some simple operations like map and filter, et cetera, back to bear in a sort of convenient way. Okay, but now our query is a little bit different. We're going to go in and start to do some things specifically related to the machine learning query, the machine learning goals here. Okay, so as I said, we're going to do things by hand at first, so you see how it gets done, and then we're going to put in place a pipeline before the sun sets, and I would hazard before the sun reaches its zenith. Okay, so yeah, don't get worried. Fraction subset 1. We're going to take half the data. We'll reserve half the data for testing and half, or for model estimation, and half for testing. Okay, half for training, half for testing. We could have done 0.75 if we had wanted to have a different balance, but we're going to do it both ways. Okay, and now we're going to do something which is going to test your recollection from an earlier lecture. Okay, I'm going to say val array df labeled subset. So we should say DS labeled subset 1, and DS labeled subset 2. Okay, equals DS all tweet text, that thing which we defined earlier, DS all tweet text. Okay, dot split, random split, and it's going to be an array. The array of how much should be in each will be given by here, fraction subset 1. This array is going to have 2 components. The first will say what fraction to have in the first, and the second is going to have what fraction to have in the second one. I don't know why they require you to specify the second one if there's only 2 components. I think you'd have 1 degree of freedom, and therefore it should only have to have you specify 1, but that's the way the cookie crumbles. Okay. Here we go. So it's an unhappy thing. Okay, random split, not I. Random split. Okay. What's going on here? What is this? Why is that on the left-hand side? What is that?
Pattern matching.
Yeah, it's pattern matching. It's doing destructuring the data. It's actually getting back an array, and it's taking it back and dividing it up into these 2 pieces. So you may remember we can do that pattern matching in match expressions. There's sort of the prototypical example. We can also do it in for loops. We can do it associated with val expressions. We could do it on the left-hand side of an assignment. So this is a very nice feature of Scala. Here, this is returning an array, and we're taking the 2 components of the array and creating these values that just take each of those components. And it's sweet. It's a very nice a syntax for taking things apart. Okay. If anyone's interested, you can look at past lectures I've given on how this is done. Basically, there's an apply and there's an unapply operator. An apply operator for the companion class of array puts things together like this to create an array. And an unapply operator takes an array and takes it apart into its pieces. And that's what this is using. It's using unapply on the array to get back out these pieces. Okay, so there we are. We have these different subsets. Let's go see how big they are, right? Let's go check it out. Count. Let's go check. 250, and the other one is similarly 250, I think. 237. Yeah. Okay. So it's not precisely that size, but it's close to it. Okay. So I think it's sorting them into them randomly as to which goes to which. Okay. Now, so we just divided this up. Now, how are these ones different than the ones we started with earlier? After all, it may seem perverse. Here we're taking apart DS all tweet text into 2 subsets. But wait a minute, just a few lines earlier, we put it together from 2 subsets with a union. How are these subsets different than the ones out of which we composed it using union?
We don't know if they're health related now.
Yeah, exactly. These guys are all mixed together they're jumbled together, health related, non-health related tweets. Okay. Okay, these ones, the first group seems to be that, but let's here we'll take a look. What is the best way to do this here? To do filter label equals 0. This dot label equals 0. Let's count that, right? And alternative, we could do a group by would be another way to do it. So we have 194 zeros and we have 56 with ones. So in short, they're jumbled together, okay? And each of these are different subsets. And therefore, they're suitable for being used for training and for testing. They don't just have only one or the other. Okay, now we are going to create our first transformer, okay? Okay. What's that?
Optimus Prime.
yeah, exactly. If any of you want to make a movie about these next few minutes, I wouldn't object. I'm not sure how many. Well, you could probably get a good nerd group that will go there. Okay, so here's we're going to create a word splitter. This is going to split text in the form of strings into words. Now, how we're going to do this is going to be indicative of how a lot of things within Spark work. Spark ML's machine learning pipelines work. So you're going to need to pay attention to this. We're going to create a tokenizer, but the tokenizer, to do its job, it's not just any old tokenizer. It needs to know certain things to do its job. Specifically, it needs to know from what column input is going to come. The tokenizer is going to get its input from the text column, ladies and gentlemen. And then it's going to get its output from the tokens. It's going to use it as its output, the tokens column. Notice how this is being done in a functional way. I mean, we're basically layering these things in. This may look imperative, like you're setting this thing, but what's happening is you're stringing these together and it's building up a specification for the tokenizer for it to do its job. I think it actually has some defaults for where it looks and where it puts things, but we're specifying this, and now it's a fully specified tokenizer. Oops. Oh, okay. We need our tokenizer. Why isn't that imported? Where is our, oh, okay. Sorry. We need to do some more imports up here. I should have been more careful. This is why I had a whole swack of them. We need to, beyond importing just ML, the things in ML, we need to load in the, here we go. Beyond ML itself, we need to do ML.feature.this and ML.be linalgebra. Oh.
The underbar doesn't catch everything under ML.
So it seems.
It's just in that one package. It doesn't dig into nested packages.
Yeah. I don't know if there is a way to do that in an abbreviated fashion to get it to recursively do that. It would be
I don't think there's
nice. Tuning, and finally, oh, not turning, and not Turing. So tuning.
I think they have it that way so you don't import too many implicits.
Oh,
They're converted all of them.
I got it. Yeah, that makes sense. And evaluation is the final one. Sorry, I should have been more. Oh, and finally, classification. Sorry, classification. There we go. Classification. Okay. That's what we want. Boom. Boom. Okay, so ML itself, ML feature.underbar, ML linalg.underbar, ML tuning.underbar, ML evaluation.underbar, ML classification.underbar. Okay. So if you import all of those, I think we should be good to go from the next, for the next thing. So here we go, a tokenizer, and that gives us a transformer that will now allow us to transform things. So in order to show how this works, ladies and gentlemen, I'd like to do I'd like to take this word splitter and I'd like to use it to transform. Okay. I'm going to put it up here. You notice it's a tokenizer. Maybe I'll put it here. Word splitter dot transform, and we're going to transform df labeled subset 1. That's this guy here that we got back. Oh, sorry, ds labeled, not df. ds. It's a data set. Data set labeled subset 1. Boom. There we go. And this is functional. I mean, we since we're not catching it, there's no real gains in that. I said show. Okay, you'll notice, what does this have new that the other thing did not have? Yeah, it is tokens. So this one, it says B is supersec, and it turned it into tokens. B, each of which is independent. B is supersec. Health is not something. Simulate that. Wow, that's, I don't know if they're getting inspired by our work or somehow I doubt it. Being sick isn't. Being sick to you coughed my cough. Yeah, Twitter. Well, I'm not full. I don't fully grok it. Okay. So now we're going to create. So that's our first transformer. It created this tokens column. You'll see how that worked. It transforms and it gets out a new data frame that it extends it with this column, which is the result of applying the transformer to the input column, right? To the text. It took its input from here and it created a data frame which has this other components. Okay, next, I'd like to create a trivial word remover. And this is going to be a new stop words remover. And it's going to be dot set input call of tokens. So that's going to tell it where it wants to take it. So it's going to take it from the tokens column, and it's going to set output call. We're going to put to significant words. Okay, significant words. There we are. And of course, they're tokens. Okay, so here we go. Here's our trivial word remover.
So does the stop words remover already know about trivial English words?
Yeah.
We don't have to give it a list of
right.
What are trivial.
That's right. It says that's a trivial word. So it knows like a or the or of, you know, or that or this or all these articles. It knows that they're trivial. Yeah, that please, students of mine, don't leave them out of your thesis. They're not trivial for me. But in terms of machine learning analysis, often they add little insight. Like if you hang your interpretation around the number of ofs, it's not going to be very insightful. Okay. Okay. So trivial word remover. Dot transform. And let's put inside, what does it take in? What does a transform take in? It takes in a what? A what?
Data set.
A data set, and it puts out a data set. So let's give it the results. Would it be okay if we just said use this DS labeled subset 1? Would that be okay? Suppose we were to say that. Would it be a happy camper? No, it doesn't have the tokens. So we need to give it something which has tokens. And this thing has tokens. You want tokens? I'll show you where to have some tokens. Okay, it's right here. So let's go put that in here. Okay, right there. See that? Okay, and now let's show that. Boom. And now the significant words here. You notice it declared being as trivial. Okay, so being sick to you, or being sick isn't. It turned into sick isn't fun. Ben feeling so sick, and it turned into feeling sick. B is super sick. It turned into be super sick. And bed all day to bed day. Okay, so I would note, if it adds wins to your sales, that it does think that simulate that is significant. Okay, so so these are some examples. Now we could go and look at this in a little bit more detail if you wanted to see those. I think we could, for example, say maybe I'll leave that out. But basically, we could look at some more examples of the stop word removed elements. Okay, so we've just shown significant words. Now, what I'd like to do, ladies and gentlemen, is to create an estimator. We've been working with transformers, and in fact, we've worked with 2 transformers, as indicated by the number of transforms. But now I'd like to start working with an estimator. Okay. Now, what does an estimator take in? Does anyone remember? What does an estimator take in? Yeah, it takes in a data set, and what does it produce? It produces a model, or it produces something that's a transformer, and a model is an example of a transformer. Okay. So what we're going to do is to create a thing called map words to presence vector. Okay, so what our goal here is to be able to judge whether a given word is present or absent in this. We're going to have a vector of words, and each element of the vector is going to indicate, is a word present, is a particular word present or not. So maybe the first element of the vector will indicate the word sick. Is it present or not? 0 or 1. The second word will indicate, today. Is it present or absent? Another one will indicate bed. Is it present or absent? The next one will indicate Scala, present or absent. Okay. Okay. So this is going to be a mapper that will be mapping words to their presence or absent. Okay, and we're going to do new create vectorizer. This is going to be a vectorizer. Okay, and we'll do set input call significant words, and the set and the output words. The output call, set output call, will be features. Okay. And we're going to specify some further characteristics. Set vocab size to be 65,536. Does anyone recognize the significance of that?
Sounds like magazine plus.
It's when Wade and I were young, it was Maxent plus. It was max int plus 1. Yeah, it's 2 to the 16th. 2 to the 16th, ladies and gentlemen. So we're going to have certain sizes of vectors, and we're going to specify, I think, a certain, okay, set min df. Count. Thank you. Thank you. Thank you. Not create vectorizer. Count vectorizer. Okay. Thank you. Yes. There we are. Count vectorizer. Okay. It would be certainly more healthy for kids if they were using count vectorizer than count chocula. Okay. I would hope it would excite them just as much, but I have my doubts. Okay. So here we go. So now what we're going to do is we're going to apply this vectorizer, this mapper, which will basically map words to the presence or absence of a vector. We're going to apply it. But this is, I would tell you that this is an estimator, okay? And what does it mean that it's an estimator? Can we just use it to directly transform a data set and get out a vector that indicates the presence or absence of a word? What is an estimator required to do its job? Before it can transform something, what does it need? Anyone remember? Sorry?
Training.
Yeah, it needs to be trained. And it needs to be trained. Does anyone remember the magic word on which it needs to be? You need to call what on it? Fit. That's right. Right? It takes in data and it produces a model. Now, this may seem weird. What? But it actually harks back to Wade's prescient point before. What is it that, so Wade earlier asked, does the stop word remover, does it know which words are trivial just in and of themselves? Or does it need information to be told that? And I said, no, it just knows. So it can be a transformer. What is it? What do you think fit is doing to this? If we fit this, if we say fit this vectorizer, what do you think that means semantically? What would it mean to fit it? Why can't we just transform it? We just say, transform this data frame. It'll produce a data frame which indicates the presence or absence of words.
We don't know what we're looking for.
We don't know which words we're trying to, whose presence or absence we're saying. So maybe we're applying it to a single tweet. And how is it going to judge with respect to what words it should be including that, you know, that it's this certain word is present or absent? Just the words in the tweet? That would be impoverished. We need to tell it ahead of time, hey, this is the set of words you got to be looking for that you're going to judge. This is the set of words. Now we can then, having done that, having fit it to this broad set of words, this corpus of words, then we could go and we can apply it to different tweets, and it'll be telling us, okay, which of these sort of universe of words are present or absent. Does that make sense? It'll tell us of all these words, the possible words, which ones happen to be in this tweet or that tweet, etc. Okay, so that's the idea here. Fitting it here is kind of telling it what words we care about. And that's almost exactly what Wade was asking about. Because in another, you know, a Spark 2, we could have imagined a situation where, you know, Spark made stop word removal, determining of which words are trivial, actually an estimator, and we'd have to tell it which words are trivial in our language. We could tell it, and then it will be ready to serve as a transformer. So that's what's going on here. So let's take this map words. This is an estimator, ladies and gentlemen. And having created that estimator, we're going to be saying fit it to a set of words. Well, what things does it need to do its job? What do we need to pass in to fit for it to do its job? What does it use as its input? Yeah, so it needs to get in a data set with what column? Significant words. Where can we find a data set with significant words? Oh, it's right here. Okay, so let's go copy that in here. Or let's better yet, this is at some point I have to fringe. Val, I'll say all significant words equals this. Boom. And then we can do all significant words dot show. We could have done that, right? Here we go. Boom. Okay. And now we can, well, oh man, oh, that's ugly. I should have called that a data set because it's a, oh, it's a data, it's a data frame. Okay. I'd have to go back. Was our trivial word remover, was this guy here? Okay, well, I'm not gonna, time is too short. I'm not gonna just fight it. This says a data frame here, so I'll say a data frame. Fine, for now. I'll go back and figure out what went wrong, why it's a data frame instead of a data set now. Okay, so, oop, what am I doing? Sorry, don't do that. I just changed the wrong one. Here we are. This should be map. Boom, boom, boom. What I wanted to do was to change this guy to be DF, all significant words, to indicate it's a data frame that includes all, I'll call it data frame all tweets with significant words, okay? There we go. There we go. So now it's a data frame. It has all the significant words. And now we can fit this based on it. See that? Okay. So if we fit it, what do you think we'll get out? What do you think we'll get out? Well, if we fit something, we'll get out it turns out a model. And a model is a what? It's an example of a transform things. Okay, now I'm lost in my Chromes. Okay, here, where's my Chrome? There it is. Okay. So this is going to give us a model, okay? And that model we're going to be able to apply as we see fit. So I'd like to call it example vectorizing model. What would the job in life be of this this vectorizing model? Well, it's going to be doing what? It's going to be, what is a model? A model is a transformer. How does it work? What do we call on it? We call, do we call fit? We call transform on it. That's right. We call transform, and that would allow us to, for example, transform data as needed to extract the words of relevance. Okay, so let's do the following. We're going to transfer some data. Now, what it's going to be looking for in order to do its transformation is also a data column of a certain type. And to sort of help you see this, I'm going to give it, I'm going to go back up here, and I'm going to go back to our earliest transformer where we applied it to DS labeled subset. I'm going to naively apply this to DS labeled subset. What do you think will happen? That, hey, I can't find significant words in order for it to be fit, and in order for the fitted model to transform, it's looking for the same column. And this is going to become very important later, this realization that, wait a minute, we have to go through a similar processing set of steps for the data for training and the data for testing, or the data for applying. And this is one of the reasons we create a pipeline. We define that whole set of operations of transforming the data successively. Okay, so here it is. Transform DS labeled subset, it's going to have problems. So we will instead give it this guy for now, because it has significant words in it. And let's go see what comes out of that. Okay, here we go. What's going to come out of it is going to have some interesting patterns. Here we go. We're going to transform it, and here we're going to see the features there. And you may be puzzled by those features. Okay. But here, the features are indicating the presence and absence of certain words, okay? And specifically, as I recall, one of the things we're doing is we're saying here, okay, in this vector of length 115, it's indicating which entries are non-zero. So here we have entry 1, entry 8, entry 93, and entry 105 being non-zero. By contrast, for this case, we have no entries being non-zero. Here we have only entry 1. Here 1, 16, and 70. This is a sparse vector. Okay, it's something called a sparse vector. And a sparse vector, rather than forcing us to say 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0 in a very wordy and space inefficient way, it allows us to summarize a vector that's likely sparse. There's only a few entries that are likely filled in some cases none, in this case 1, in this case 4, in this case 3, here also none, here 1 and 1. Okay, so this is a sparse vector. Okay, so what we have done is to show that. Now, if you'll allow me to, within 5 minutes, we can produce a logistic regression that operates with this. I recognize some of you may have to go, but I think what I will do is just sort of cap off our session with this. I have to be cautious because I need to have a meeting over at my office, I think. But so what I'm going to do is we'll just see how we can define a model here, and specifically a model pipeline as well. Okay, we're going to say logistic regression equals new logistic regression dot set max iter, okay, 100,000. Okay, this is that's a million. It should be 100,000 10 to the 5th. Yeah. Dot set reg param. These are these notion of parameters that we'll come back to. And Spark provides this, Spark ML provides this nice way of sort of dealing with parameters explicitly by reifying them. Set max iter here. Oh no, we've already done that. Set tolerance. This is another parameter which is used, and we'll see how we can examine the impact of different values for some of these, and set standardization to be true. Okay. That's our logistic regression. Now, our logistic regression is going to be an estimator. Why is a logistic regression an estimator rather than a transformer? Doesn't a logistic regression just take in data and classify it? Well, sort of. Before we get the logistic regression model, we have to estimate it. We have to create it. We have to define a particular logistic regression model. Same thing for, you know, many other types of machine learning algorithms. So next, we're going to define a logistic regression pipeline that's going to remove a lot of the tedium we had to deal with above. Here, new pipeline, set stages, and the stages are going to be specified with an array, and the array is going to specify successive stages. So the first thing we're going to do on any raw data is do a word splitter. The second thing we're going to do is to do a trivial word remover. The third thing we're going to do is to map words to presence vector. Okay, here we go. Map words, trivial word remover, map words to presence or absence vector, so to present vector. And the final thing is the logistic regression. This is an estimator. It needs data to estimate the regression to produce a transformer. And therefore, the pipeline as a whole, like other pipelines, is an estimator. Okay? It works, it needs data to produce, to be fit to it, to produce a model, which can then serve as a transformer. And here we go. And so we're just about done here. We'll have logistic regression pipeline. That's the estimator. And so in order to get a logistic regression model, we're going to take the logistic regression pipeline and do what? Logistic regression model is a transformer. So what are we going to do with the estimator? Oops. What do we do with an estimator to get a transformer? We fit it. We fit it. And right now we're going to say DS all tweet text. Okay, tweet text. Next time we're going to do some cross-validation. Here we are. Well, what the heck? Maybe I'll say DF. What is it? DS labeled subset? Or is it DF labeled subset? Which one was it? I'm doing autocomplete.
Yeah, labeled subset 1.
Labeled subset 1. Is that right? Here, I'll try that. I said DS labeled. Maybe for you it's DF, but I did it DS. Okay. Okay. So we've just fit it to one subset. And now, having done that, what do we get out from the fit? We get out a what? A transformer that we can transform. So this is now a fully estimated logistic regression. When we specified this subset, it applied all these stages of the pipeline. It applied word splitting. It applied trivial word remover. It mapped words to presence vector, performed the logistic regression to estimate the logistic regression. It fitted the logistic regression to that data that came out of here, of these stages. And that gives us a fully qualified logistic regression model that can now be used, ladies and gentlemen, to judge each tweet as to whether or not it's health related. Okay. whether or not it was indeed health related. And so, for example, we could do show here, and it's going to have a prediction of occurrence here. Okay. And separately from that, there's a label 1.0. So this is labeled 1. It was predicted as 1. This is labeled as 1. It was predicted as 0. And then finally, we will do a val binary classification evaluator, which is a new binary classification evaluator. Binary classification evaluator. We can set the metric name to be set evaluator. We can set metric name to be area, under the ROC curve, the receiver operating characteristic curve. That will judge how effectively a job it's doing in classifying. We'll set the raw prediction column to be what's called raw prediction. And we'll set the label column, set label call to be label. And those names reflect the raw prediction here and the label column here. This is what it predicted, and this is the ground truth. We will provide that. And now we simply, having set up that evaluator, now we just have to take that evaluator and evaluate the logistic regression from the pipeline. And it will it'll judge that. So this logistic regression from the pipeline should have been here from this transform. So val df logistic regression from pipeline. Here. Should have saved that away. And now I can evaluate how good a job it did. I'll say dot evaluate, and I'll say logistic regression. Oops, hey, come on. Sorry, df evaluator dot binary classification evaluator. Okay, so why is it not okay? So, oh, of course, I said show. There, this is why. I should have done this and then show. Show. And now we can do this, and it will give us how good a job it does, which is the ROC area under the ROC curve, which specifies how effectively it's classified. Okay, I need to turn into a pumpkin. In fact, I think I am a pumpkin already. I've just got to check where this is. Yes, it's in my office. Okay. And we will come back to this next time, where we will be using these pipelines more, and we'll see how we can perform cross-validation, how we can perform cross-validation automatically, and how we can set up parameter sweeps of different parameters to identify best parameter values. Okay. Thank you very much for your patience, and I will see you next time. And I will post this this exact work that we've done. Oh, okay.
So I need a I need a table.
Yeah.
From Schema 10 that there's no in Cassandra.
You need a table for.
There is a table on Schema 10 on SQL,
yes.
MySQL.
Yes.
This table, it's not presented in Cassandra.
It's not in Cassandra.
Yeah, it's not in Cassandra. So what